Okay, I think we're recording. I think it's happening. All right, so like I said, we're going to look at the second part of the adaptive immune system. So in the past, I guess we have talked about the innate immune system. Okay, so we said the innate immune system is essentially a generalized immune system. Yeah, so if we get some sort of infection or disease, our body tries to fight that by essentially undergoing either a body-wide defense, like if we have a fever, it tries to raise our body temperature across the whole body, or if we get a cut, it will try and, I guess, attack the pathogens that are infecting that particular site, but it will attack all pathogens by the same means. Yeah, everything will be the same. Okay. Then we started looking at the adaptive immune system, and we said in the first sort of section of the first part we looked at, we talked about, I guess, some of the looking at different lines, and this is our third line of defense, or the third line of our body defense, looking at how the adaptive immune system involves specific sort of antigens of specific pathogen recognition. Yeah. Okay. And we said when we get infected by something, we undergo some sort of immune response. And then if we're infected again, we undergo a secondary immune response, which is a lot more effective and a lot quicker. Okay. We looked at some of the mechanisms of antigen recognition. We looked at some of the idea of how we have presentation of the antigens on the outsides of macrophages in order for our body cells and our immune cells to actually recognize infected cells and kill them off. We talked about our B cells and our T cells, which are our lymphocytes, which are part of our adaptive immune system. Yeah. Okay. Let me just get rid of that so that goes away. All right. And we talked about cell-mediated versus humoral immunity. Yeah. So we're going to talk today, though, about the second part of the immune system. I know for some of you who have already gone through it, I apologize. If you've gone through sort of the majority of it, I do apologize for that. But I'm going to have to go through it myself again. Yeah, well, I want to go through it because I like to discuss it, and we'll see how we go. Right. So we're talking about acquired immunity. So this idea of specific immunity, we said that it comes in sort of two variants. We have natural immunity and we have artificial immunity. Yeah. Okay. So obviously, natural immunity is being either exposed to a pathogen or a disease ourselves, and we gain immunity from that. Artificial immunity is sort of, I guess, immunity via outside help. Yeah. And so we get either technological advances have allowed us to create some sort of artificial immunity. Yeah. And each of these types of immunity are also broken down into what we call active or passive immunity. Okay. Now, what do we mean by this? So we said natural is acquired through sort of normal exposure. It's not by any sort of medical means. Yeah. And, a couple hundred years ago, this is all we had. We really only had natural means of immunity. Over the last, especially over the last sort of 50 or so years, artificial immunity has really taken over and it's become a large thing. And it's helped a lot of people. Yeah. It's saved a lot of lives. It's not perfect yet. Mainly because of the nature of disease and the nature of viruses and bacteria. They're constantly changing, and we're trying to adapt to that. So we are getting better in the artificial realm, but it's still not a perfect sort of system yet. So like we said, natural immunity is by sort of a natural, or I guess by a pathogen that's entered the body naturally. Yeah, but there are two variations of that. We have natural passive immunity, okay, or sorry, natural active immunity where we're actually infected. Yeah, so that's the standard way. So at the moment, if we think about, even like influenza or whatever it is, if you go and catch the common cold or you catch the influenza virus, your body will mount an immune response to that. Yeah. Okay. And over time, once we've overcome that initial, primary immune response, we have some sort of immunity to that disease because the secondary immune response is so much better. Yeah, so when we are, I guess, infected by the pathogen, we develop immunity from that. So that's natural active immunity.
I got bitten by 2 pit bulls, but when the dog bit him, it bit him in the jaw or something.
Yep.
And it had some sort of it was from overseas, the dog, and it did something to his chin, and it, I don't know, it sort of caved it in and made a disease in him somehow.
Yeah. Okay. Yeah.
The chin was the same replica as the disease, the replication.
Yeah. So generally, if you get bitten by an animal, animals
That's
tend to
what I'm
have a lot
worried
of
about when
disease.
I got bitten by the 2.
Yep.
I just got out of hospital again, but for air in the lung, so that'll be all right.
Yep.
And yeah, so I had the tube in my lungs, so I went under and different funny colours and
Yeah.
straight out. Yeah, had
Yeah.
about 2 or 3.
Being bitten by animals is a pretty easy way of gaining infection because they tend to have a lot of bacteria and stuff on them. So yeah, it's not a good thing. So yeah, if we think about natural active immunity, that's where our body develops its own immune response to a pathogen. It's pretty the standard way we get infected and we create our own immune response. Okay. Natural passive immunity is, you got to remember, when we develop or when we undergo an immune response, what happens, right? Well, is that, I don't think that is not what I want. If we undergo an immune response, right, we have some sort of pathogen which infects us. And what does our body do to overcome that and to create immunity for future generations? We produce antibodies, yeah? And we talked about how antibodies are specific for that one type of pathogen. And the antibodies then allow our body to kill off the pathogen, yeah? In natural passive immunity, these antibodies can be transferred from one host to another to give us immunity, but without our body actually undergoing the immune response. Because in order to create our own antibodies, we need to be infected by the pathogen, we undergo the immune response, and then we produce our own antibodies. Yeah, that's what natural active immunity is. Passive immunity is where we are just given antibodies directly. So we haven't actually created our own antibodies. We're not technically immune to future infections via that disease because we haven't undergone the immune response. We haven't created B and T cells that can create our own antibodies yet, but we do get antibodies via either our mum gives us antibodies through the placenta, yeah, so we get protection from our mum. Okay, so if we have newborns, they can give it to us through the placenta and also through breast milk. Breast milk's a really good source of antibodies directly, and that's why they say, if possible, it's best to breastfeed your children because you can give them some protection initially. So those first few months as a baby, your immune system is pretty much non-existent. So this is a way of giving some protection. Yeah. All right. So that's what we mean by natural passive immunity. It's not by a medical means. It's still a natural process. All right. But it's passive because we're not mounting our own immune response. Okay. We're not producing our own antibodies. We're just being given antibodies directly by our mother. Okay. Some animals, plants, and things do have genes that provide some sort of natural resistance to disease also. Okay. And that's sometimes sort of it can be really, yeah. So a lot of dogs, for example, can't get, like human diseases, and certain animals, they can't get certain diseases. They might just have some natural resistance. That's sort of also another idea of natural passive immunity. Yeah.
Must have been already from that country we didn't know, maybe.
What's that?
That guy with the jaw that bit.
Yeah, it might have been. Yeah, so over.
But didn't know.
Probably.
That must have
Yeah,
been
probably not. Okay, so natural, like we say, is either infection via a pathogen or being given antibodies via our mothers. Artificial immunity is via medical means. Yeah, so we are gaining immunity by some sort of medical means, and it can be either active or passive again. Now, remembering active still means that we're generating our own immune response. That's what active means. Active means we're generating our own immune response. We're producing our own antibodies. Okay. We're producing B and T cells that will fight, that will produce the antibodies. Okay. But rather than being infected naturally by a pathogen, we are then intentionally exposed to the pathogen. Yeah. Okay. And that's still going to undergo the same immune response as if we were infected naturally. It's still exactly the same. Okay. And this is what we call a vaccine. And this is why we get vaccines. They just mimic a natural immune response. Okay. And we undergo immunization via a vaccine. Again, artificial passive, same thing. Passive still means we're being given antibodies directly. Okay. So passive means we're given antibodies directly. We're not undergoing our own immune response. Okay. We're just being injected essentially by antibodies to that specific disease. Yeah. And this is the basis for antivenom or antivenoms. Yeah. So if you get bitten by, say, a snake, all right, the snake has toxins which enter your bloodstream. Okay. The problem is you can't go and get a vaccine for that toxin because a couple of reasons. It's too slow. You've got to remember, if we look at the primary immune response, that can take up to a couple of weeks, right? If I get bitten by a snake, that could kill me within hours potentially, yeah, or like over a day or two. So there's just not enough time to be given a vaccine to undergo your own system to produce your own antibodies. You won't have the time. So what they do is they bypass all of that system where we create our own antibodies and just pump antibodies directly to neutralize the toxin that you've been infected with. Yeah, and that might be a snake, a spider, or a scorpion. Okay. But again, at the end of the day, if we think about it logically, active means undergoing the immune response. Okay. All right. Now that can be natural, where we're infected with a pathogen, or it can be artificial, where we are, exposed to the pathogen in some way. But in both cases, you're still undergoing the same immune response. You're still undergoing the primary immune response. You're still producing antibodies. Okay. Passive, in both cases, you're just given antibodies directly. Okay. But because you have not produced your own B and T cells through the immune response, you're not immune to future, infections via that toxin or pathogen. Okay. So if you get bitten by a snake or whatever, you might eventually, if you're just injected with the antibodies for a specific toxin, doesn't mean that you're going to be immune to future infections via that thing. Yeah. So they're a really good, sort of real quick, short-term solution. They will neutralize the toxin, but it's not good for future, exposure to a pathogen. Okay. So let's talk a little bit about this idea of artificial active. All right. So this idea that we are intentionally exposed to a pathogen, okay, and we are intentionally exposed via a vaccine. Okay. And these are just any materials that's going to stimulate the productions of antibodies, but not only antibodies. The key here is the lymphocytes, those memory cells. Because if we can produce memory cells, that gives us future protection against these particular pathogens. Okay. Now, vaccines can come in a range of different forms, because you've got to remember, we will develop an immune response against any foreign particles that are going to cause us harm. Okay. So they can either come in the form of the entire pathogen, but in an inactive form. So they might kill the pathogen via heat, but still inject you with the pathogen. Okay. All right. There might be a less active form of the pathogen, so one that's not necessarily going to cause disease. It could still be alive, but a lot of times what they'll do is they'll They might take away its ability to produce a specific toxin. They might take away its ability to enter specific cells. So they modify those pathogens to make them less, active or less virulent. Yeah. Okay. But you're still going to produce the antibodies in the exact same way. All right. They might be antigens from the pathogen, because remember, the pathogen will have antigens on the outside. So what they can do is they can harvest these antigens directly and then put them into your system. You'll still produce an immune response. It's still fine. It still works. Okay. Or they might actually give you an inactive form of the toxin that's released by the pathogen. Okay. You'll notice in all 4 cases, though, they can't cause you the disease that the pathogen generally causes, because it's either inactive, it's either just the antigen. The antigens aren't going to cause a disease. They could be inactive, or they could be a less active form. But in all cases, you're not going to get the disease that you're injected a vaccine from. This is not going to happen. Okay. The idea, though, in all 4 cases, the idea is to stimulate the primary immune response. Okay. And the immune response will be exactly the same as if it was natural, and if you were naturally infected by that pathogen. It's no different. Okay. All right. So in the first case, the primary immune response will destroy the pathogen in the vaccine. So the same thing will happen.
It's like passages in getting immune when you get held, basically.
When you get held by
a doctor or any GP or.
Yeah. So like they can give you the vaccines. Yeah.
Or vaccine, yeah.
Yep.
But it matters in dosage or what's going on with yourself, though, doesn't it?
Yeah. So doctors have to be careful about what types of vaccines they administer, and yeah. Well, you got to be careful if you have a compromised immune system. They have to be careful with vaccines sometimes. Okay. So they do have to be careful. I'm not sure. So you can imagine, like, if I get the common cold virus, for example, our primary immune response will destroy the pathogen. It's no different in a vaccine. Your primary immune response will still destroy the pathogen in the vaccine. You're going to produce memory T and B cells. Okay. And the idea there is that once you produce those memory cells, if you're infected again later on by the same pathogen, your body will undergo the secondary immune response, which is a lot more rapid. Yeah, and it can happen over a couple of days. And in most cases, you won't even get any symptoms from that particular pathogen. Yeah. All right. So it's no different than being naturally infected. It just means that you're not going to get the symptoms of the initial, disease from that pathogen. All right. And this has been going on for a long time. There's been certain, variations of vaccines for a couple of 100 years. Okay, they obviously weren't quite as, as safe a couple 100 years ago, but they are very effective at limiting the spread of disease within a population. Okay, and you can see, just like the coronavirus or the COVID-19 virus at the moment, is a really good case study of just how fast viruses can travel when we don't have access to a vaccine. At the moment, this is a new virus. We don't have a vaccine for it. And you see countries, Italy and America, it is just spreading so quickly because nobody has immunity to it. So anyone that comes in contact is potentially going to get sick from it. Yeah. Okay. If we do have a vaccine, it's really important that everyone in a population gets vaccinated. Okay. Because the idea is, you've got to remember that diseases are spread via contact. Within this room, if all 4 of us are vaccinated, it doesn't matter if somebody walks in with that disease, we're not going to get the disease, right? Great. Okay. And it means we're not going to spread it to someone else. Fantastic. Okay. All right. If no one is vaccinated, it's going to spread really quickly. That's what we're seeing now with the coronavirus. It's spreading rapidly. Okay. If some of the population is vaccinated, it can still spread. Like if one of us were vaccinated and the other three were not, it's still not going to help too much. It's still going to spread between three of us. You know what I mean? Okay. However, the idea is that it's not always feasible for everyone in a population to be vaccinated because some people might be compromised immunity, so they may have a sickness themselves. Okay, it might not just be financially viable. There are a range of reasons why everyone in a population can't be vaccinated. However, if the majority of individuals are vaccinated, it's a lot less likely to spread. Okay, and this is what we call herd immunity, where if a certain percentage of a population are vaccinated, you can almost completely stop the spread of the disease. Yeah, and this is sort of what we're seeing within South Australia, for example, to a degree with this coronavirus. It's not necessarily that we're vaccinated, but because the majority of people are staying home and they're isolating, it's working in very much the same way where less exposure to less people has actually stopped the spread of the virus because it doesn't have enough people to latch onto and to spread to other people. Yeah. And so the idea is if we have a large portion of the population that's immune, it just stops the virus from being able to jump and latch on to different people and spread throughout the population. And there's a range of different case studies. And this is just a sort of a picture that online that sort of tries to show just how quickly a virus can spread at different vaccination levels. If 0% are vaccinated, every single one of these dots will get infected if somebody next to them has it, right? And it just spreads. There's nothing to stop it or slow it down. Yeah. If 25% are vaccinated, so about a quarter, doesn't really make much of a difference because if one out of every four people are vaccinated, three are not. And so if I've got it, even if, Brendan's vaccinated, you two are still going to get it and you're going to go and spread it. It doesn't really help. When you start getting to 50%, you can see it can slow down the spread. It can work to a degree, but realistically, they say that you should get at least sort of 75% is like the minimum. 90% is really effective. When you start getting to 90% vaccination, the virus has almost nowhere to go, and eventually it will hit a point where it just dies out because there's not enough people to infect. Yeah. All right. If you get to 95%, you'll notice the people that are not vaccinated are so few and far between, the virus can't jump from person to person. And so it's going to stop. Right? There's just nowhere to go. All right. And this is what we call herd immunity. And the less people that are vaccinated, the worse it is and the more spread. And this is why it's so silly for people to not adhere to social distancing. And you see people, especially interstate, you go to places like New South Wales, all those people went to like the Bondi Beach. There's thousands of people, and it's like the problem is you get a group of those people doing that, and you're just facilitating the spread so much quicker. Whereas SA's done a really, really good job. We were pretty quick on it to start with. We've isolated pretty well, and you can see just how critical and how well we've done. We've had 4 days of, I think, no cases or whatever it is. So we're doing really, really well in SA because majority of people are adhering to the rules. Yeah, that's part of it. It's also population density. So how many people are in certain areas? Okay, where we're lucky in SA. In SA, these dots are further apart, so it's harder for the virus to spread. I think I was reading, what was it? I think out of the average people per square kilometre, I think in Sydney it's like 400 people.
Like maybe what they say on Curiosity at the end, if you're really good at science, the noose, is that like a total thing or is that just something?
What do you mean by that exactly? I'm not sure what you mean.
When you're fully healthy and you
Yep.
get tested and you have a combined testing and you have a result,
Yeah.
yeah, is that still a theatre or is it still worse? Or is it...
If you So if you're healthy and you get tested for what exactly?
Or once there was that, say, bipolar or whatever it is, or that one was, or maybe just rabies or something from
Yeah,
your yard or someone from
yeah,
your yard or here and there.
yeah. And if,
Yeah.
yeah, and if you're
Probably,
tested, then what?
you could probably rub it off anyway, but you know what I mean? Like,
You got to be careful. Like, yeah, and that's what I'm saying. Like,
if you, yeah, you probably
vir-
have to be
viruses can stay on surfaces for a long
protected, of
time.
course, right? But anyway,
Yeah,
yeah.
but yeah. So you got to remember. Yeah, I think in Australia we're about 400 people per square kilometre. In New York, it's about 18,000 per square kilometre or something stupid. So just the population density is crazy. Just means their dots are closer together. It's harder to isolate. SA is pretty lucky. We have a pretty good population density to stop the spread of diseases. The issue is, okay, so we can be vaccinated, right? Remember, a vaccine, remember the whole point of adaptive immunity is we're immune against one specific antigen, right? One specific pathogen. So if this pathogen has some antigens on the outside, we're exposed, we produce antibodies that are directly against those antigens, yeah? The problem is pathogens can change also, and they can mutate. And what happens then is those antigens change, and they don't have to change a lot. They can change slightly. Okay. Once those antigens change, we no longer have immunity because we're not producing antibodies against the new antigen. Yeah. So the flu, for example, is constantly changing the antigens on the outside of its capsid, and this is what we call antigenic drift. So antigenic drift is one specific pathogen changing its antigens. Yeah. All right. This makes it really hard to immunize against because the flu is changing so constantly. We create a vaccine, which takes a long time, and all of a sudden it's different. We've got to create new vaccines. So each year we have to make sure we get the flu vaccine every year because it keeps changing. And there's about 100 different strains of the flu, 100 different, or over 100. There's a
Yeah,
lot
does
of
the
different
software
strains.
have like a client or a numbered or a lettered client name for all them things?
Yeah.
Dutchery or something?
Yeah,
Yeah.
there's heaps. Yeah.
Yeah.
So each year, each vaccine covers about
Mm.
4 strains of the flu
Yeah.
virus or something, and it covers like the main ones. Yeah.
Mm.
So we can get antigenic drift, which is the changing of one pathogen, uh, or you can get what we call antigenic shift, which is where two different viruses join together to create a new one. Yeah, and these are the most dangerous because they tend to create viruses that are hybrids of animal and human viruses. The problem is from that is that the animal virus contains things that our body doesn't recognize at all, and they can be quite deadly. Yeah. Okay. So, and that's what this COVID-19 one is. It's sort of a combined. They think it's a combined virus, and it can be very, and that's why it's quite a deadly thing. Majority of like the main pandemic or epidemic viruses are combinations of animal and human viruses. So they tend to be the most deadly. Yeah. So this is what we call antigenic shift. So you have antigenic drift, which is the changing of a single virus. Antigenic shift is the combination of two viruses. Very deadly, not very nice. Yeah. Okay. Vaccines, some protect for life, some you need boosters for. Okay. Um, and it just means that you need additional vaccines down the track because a lot of times our B and T cells can actually die off if they're not being activated enough. They can die off. So tetanus, for example, uh, it's not that the tetanus pathogen changes. It's just our B cells and our T cells die off that previously recognized. So we have to keep getting boosters about every 10 years. Yeah, and there are, especially when you're younger, you need to get multiple vaccines of the same one. You 2 or 3 booster shots to become fully immune to a specific pathogen. Yeah. let's have a bit of a look at a case study. So if we think about polio, so polio is
That's what I
this,
was saying before, but I don't think. Yeah.
maybe, I doubt it. Yeah.
Yeah.
So it's this disease which it's caused by a virus invading the nervous system and pretty much stops the nervous system from working. It's a pretty horrific disease. It can kill the patient. Usually, children under 5 years of age get killed off, but can cause sort of lifelong paralysis. Yeah, we can't cure polio, but we can vaccinate against it. So if you get it, we can't cure it, but we can stop it from happening. Yeah, and so there's been big pushes to vaccinate against polio, and we have actually done really well in terms of eradicating it. It used to be,
They say it was when they reported people in another country with their process.
mm,
They had it as like I think it was like as like those countries they went and looked at the rods
yeah,
like of those certain countries, all the siege like channel ones,
okay,
but they didn't not say that it was a grade of like deering, like
okay,
daring and things like
yeah,
so whatever that is in life is no good.
yeah, okay,
So there and where and stay healthy.
yeah,
You know what I mean? I
yeah,
thought it was really good.
yeah,
I expecting because like
mm,
most people who watched it would probably had glasses and that.
yeah,
And you don't watch that.
yeah,
You don't need to see that.
yeah, I
So
know,
like they'll dissolve that and you'll just live on. You know what I mean? Like
yeah,
mum and dad would
yeah,
if and how and why not.
yeah,
Your our son or something.
yeah.
Like that.
Information's an
Love it.
incredible thing.
Yeah,
Yeah.
I like that.
Because you look back from like, if we think about even just 1988, so, we're talking about 30 years ago, polio was pretty spread, right? It was pretty endemic in a lot of the parts of the world. It was spread across, particularly sort of Africa, all through sort of Asia and Europe. It was pretty widespread. South America was hit pretty hard as well. Okay, over the course of 30 years and through vaccination, we've pretty much got it down to, and this is even sort of 8 years old now, so this would be even less than what it was, but down to just a few countries spread throughout. Very, very little. Okay. Um, there are regions that are obviously the majority now of the world is polio free, right? So we think about, Australia, America, majority of sort of Europe and Asia are actually polio free. There are some areas of Africa that still have polio, well, they did, which is sort of being eradicated now. But yeah, so you can see just how much of a difference vaccination made over sort of 30 years. And you think about the number of cases that we had. Okay, this is sort of thousands of cases. So in 80, back in sort of 85, we're looking at almost 400,000 cases of polio. All right, now we're down to, I think, about 250 or 280 or so, and that was sort of 6 or 7 years ago. So we made a really big, back in 1988. They made that resolution to eradicate polio, and over the next sort of 10 years, we made, just by vaccinating and making sure the information was out there, and information's key. If people know about it and they know what they're doing, and also resources in order to get that, I guess, the vaccine out there, can make a big sort of decrease in in reported polio cases over sort of 30 years or so. And so we can see that, the number of countries which are polio free has increased. Almost no countries still really have the wild polio virus in their population as an endemic thing. Yeah. And so we went from sort of that 400,000 estimated cases to less than 300 cases. So about a 99% decrease over sort of those 30 years or so. Yeah. So in 2013, really only 3 countries, so Afghanistan, Nigeria, and Pakistan, were polio endemic, which means it's pretty widespread in those countries. But 3, down from more than 125, about 10 million people are walking today who would have been paralyzed if we didn't have that vaccine available. So we've made incredible strides just through the use of vaccines. Okay. So vaccines are really good against viruses because viruses have those antigens. We use vaccines for viruses. Okay, bacterial infections are a little bit different. We tend to just use antibiotics for bacterial infections. Okay, all right, and these are just compounds which stop bacteria from growing. And there's different classes of antibiotics, and they all do different things to stop the bacteria. So they have different modes of working. All right. So for example, beta lactams stop the cell wall from being formed. This class of antibiotics stop the DNA synthesis within bacteria. This class stops protein synthesis. So all of these antibiotics work in slightly different ways. At the end of the day, the key is to stop bacteria from growing. That's the key to it. Yeah. Okay. Keeping in mind, antibiotics don't work against viruses, and that's why we need vaccines and we need antibiotics working in conjunction. Okay. And a lot of times we tend to overuse antibiotics, and this can lead to antibiotic resistant bacteria. Okay. Which is a pretty big issue at the moment. Okay. And this is why it tends to happen, because you've got to remember, in bacteria, we still get mutations. Just like viruses, we said in viruses we get mutations, which produce different antigens. Bacteria also mutate. Okay. This mutation leads to different proteins being produced. Okay. And eventually, if you get enough bacteria mutating, producing a random proteins, eventually one of those will be able to resist the action of the antibiotic, and it's pure chance. Yeah. Okay. You know, it's just a total chance thing. Eventually there'll be one bacteria that has some natural resistance to the antibiotic. Okay. So for example, in certain bacteria there is an enzyme which actually destroys this particular class of antibiotics, the beta lactams. It actually destroys those particular class. So penicillin is an example of beta lactam, a beta lactam antibiotic. So there are certain bacteria that produce an enzyme or a protein which stops that from working. Okay. And you think about it. Okay, so if I have a bacterial infection, what do? I have antibiotics. Fantastic. Kills off the bacteria. Great. All right. However, if I have 100, bacteria in my system, and that drug works against 99 of those, great. Okay, but there's still going to be one left over that is resistant. Okay. And what's going to happen is that before you had 100 bacteria, so they're all competing, all of a sudden you've got one bacteria, there's no competition, so they divide really, really quickly, and they can actually grow very, very quickly. Yeah. And so they can form a population of what we call superbugs, which are the cause of a lot of deaths annually. Yeah. And it's becoming more and more prevalent at the moment, this idea of superbugs, because we're, as a society, we tend to overprescribe antibiotics pretty quickly. Oh, you're sick, antibiotics. And you got to remember, even the common cold is a virus. It's not going to work. It's not going to work against, the common cold. So we don't want to give antibiotics out too readily. I've got just a short video here. Now, give me a second. This isn't working as well as I wanted it to. I'm just going to just pause that just for a second. I'm going to change over the sounds part. Just got a short, it's like a 2 or 3 minute video around superbugs. Let's go with digital output, set as default. Okay. Okay, so that's better. And then we'll be done for the moment. All right.
In his book, Microcosm, Carl Zimmer says, there's an old saying about death by 1,000 paper cuts. But what if it just took one? That's silly, right? I mean, even if this did get infected, we've got antibiotics to clean us up, as easy as aspirin.